All right. How is everybody? Go Bombers. My cousins were Bombers. Yeah. Oh, very nice. Yeah, so the mascot of the Richmond Bombers is a mushroom cloud from a nuclear bomb. So kind of unique. So who would like to offer a prayer for us? Go ahead, thanks. Amen. Thank you very much. Your homework, do the 4.4 written and study for the exam. Next time, we're not covering a new section, so you don't have videos to watch or sections to read. So please study. There are practice exams up. There's even a review sheet this time. I think we have a total of 4 practice exams. And I'm going to strongly encourage you to do this. So keep one of the practice exams, don't look at it until you've studied and you feel like you're ready for the exam. And then take that practice exam like it's the exam. You don't have your textbook with you, you don't have notes, you're not looking up things on the computer, you're not asking anyone else. That is a really good test of if you know how well you know the material. And then you can look and see, you can look at the key and see how well you did and see where you're still struggling and you could study more. Often what happens is students only study and only work with all of their other resources around. You've got the textbook, you've got the computer, you've got a calculator, right? You've got your notes, and you study and you go through the practice exams with all of those things, and then you get to the exam and you think you know it, and you do in that situation. You could have ways to figure out the answer, but then you go to the exam, you don't have those resources, you don't know it as well as you hope. So it's a really nice test to make sure, like, hey, do I really know this well enough to take the exam? And with 4 practice exams, you should have plenty to study and then still leave one of those. The exam starts on Wednesday. It'll be like the last one. It'll be on Gradescope, and ends on Friday. So, any questions? Okay, so go ahead and work on these problems here. And so you're trying to figure out what linear transformations do these matrices do. And I suggest you might want to calculate the eigenvalues and eigenvectors to help you think through that. And then once you've done that, discuss your ideas with a neighbor. I already did A for you up here for finding the eigenvalues and eigenvectors. I'm just going to rewrite my work up here with a different color. I know that's weird. All right. So let's talk about A first. I did the work in blue in A. So someone tell me what the transformation that A does to a point or to a vector or to the whole plane. It's all the same thing. Yes, over there. And the x-axis stretches it by a factor of 2, okay? Y-axis stretches it by a factor of 4, okay? Questions about that? Okay, pretty straightforward. All right, what's the transformation that the matrix B does? Isn't that also straightforward? Just kidding, I know. It is if you think about it the right way. So does someone have a nice way of thinking about B? Let's go back here. I heard you talking before. I thought you had a nice explanation. So go ahead. Once you find the eigenvectors, which are 1, 1, and then we got negative 1, 1. I guess it doesn't really matter whether you do negative 1, 1 or 1, negative 1. It's those lines. So once you have those and you know by what factor they're stretched, then for instance, if you just pick a square shape to start with and then apply the transformation, the two top right and bottom left corners would stretch by a factor of 2, and then the bottom right and top left would stretch by a factor of 4 along that line. Okay, here let's just talk about it in the same way that we talked about the blue ones. Okay, so if we think about these two vectors, these are eigenvectors. What happens to this one when we do the transformation? Stretches by a factor of 2. Okay, and what happens by this one? Stretches by a factor of 4. Okay. So do these matrices do the same transformation? Yes. Or no? If I pick a point like 2, 0, and I multiply, and I put 2, 0 over here and 2, 0 over here, and I multiply it by, like here I get 4, 0, and here I get 6, 0. 6, 0? Nope, I get 6. Oh, I'd still get 4. Okay, is that a bad example? So 2, 1, 2, 1. Okay. So here, what do I get? Do I still get 4? Here I got 4 and 4, and I get, yeah, I get 4 and 4, right? What do I get here? 5, and that's enough to know that it's not the same. Okay, so in some respects, they're not the same. Like, if I pick the same point and I multiply or apply both those transformations, I don't end up in the same spot. So how can you say they're the same? Yes. So he said, well, those are two different coordinate systems, right? So if you had the same point represented in different coordinate systems, or maybe like if you had a point that was 1, 1 in one coordinate system and 1, 1 in another coordinate system, and applied the transformations in the respective coordinate systems, would you end up in the same spot? You won't end up in the same, they won't end up in the same spot on the board, but they might end up in the same spot if you think about them the right way. So here, help us think through this. So yes, in some sense, they're the same transformation because they both stretch the first eigenvector, and they both stretch in the direction of the first eigenvector by a factor of 2, and they both stretch in the factor of, in the direction of their second eigenvector by a factor of 4. That seems to be the same, but the eigenvectors they're not pointing in the same direction, so you don't actually end up at the same points. You start with the same points. Here to help us practice this, I have a little activity for you. So there's a point P. The question is, by thinking about transformation, so we're not going to do calculations. We could, of course, take the coordinates of P, think about it as a vector, multiply it by A and multiply it by B, and we could get things. But we don't want to do that, okay? If you just think about the transformations that happen with A and the transformations that happen with B, where does P go with those two transformations? So think about that for a minute and then talk to a neighbor. So go ahead and start talking. All right. Okay, let's start with P again. Let's start with the blue again. Who can tell us, just thinking about transformations, where P is going to end up if we multiply it by A? Come on, I heard lots of talking. You can do this. Ian? Why 212? Okay. Okay, so I'm 1 away from the x-axis in this direction, so I multiply that by 2 to get over here. It takes 3 of these other basis vectors to get to P, and so I'm up 3. I need to multiply that by 4, because that's what I do in this direction. That's what the eigenvalue is. So I start it by 4, I end up at 12. So 212 is what you got. Okay. People get that in any other? Did you get anything else? 212 seems reasonable. Okay. So again, a slightly different way to think about it is the coordinate here for P is one of the first basis vectors and 3 of the second basis vectors. So it's 1, 3. The first basis vector, I double to get 2. The second basis vector, which is 3, the coordinate of this, coordinates of the second basis vector is 3. So I have to multiply it by 4 in that direction. So I get 212. All right, now who thinks they can do the green? Who has a good, nice way of thinking about the green? Were you raising your hand? Yeah, but you already did 212 for us. Let's see if there's someone else. So, okay, right here in the yellow shirt. -1,9. Why -1,9? Okay. Someone have a way to explain this? So you raised your hand.
Along the green axis that gets stretched by a factor of 4, it's if you look at point P to that axis, it is 2 of those diagonal squares away, whereas compared to the one that gets stretched by a factor of 2, it is 1 of those diagonal squares away. So it's like.
Okay, so hold on for the people that are on. So he's saying it takes 2 diagonals to go from P to this axis, and it takes 1 diagonal to go from here to this axis.
Right. And
okay.
So that's like with that, if you consider like a diagonal portion of the square to be 1 unit, just for sake of having units, then you know that, okay, it's starting along the factor of 2 axis, it's starting at 2, so it's going to go to 4, it's going to get twice as much. Then along the factor.
Wait, okay, hold on. So you said it's starting at 2. So 2 meaning like it takes it takes me 2 of these,
right?
2 of these, and 1 of these to get to P.
Right. Yeah.
Okay, so 2 of these diagonals, 1 of these diagonals.
Yeah.
Okay, so now you're thinking about, okay, well then in this direction where I have 2 of those, what do?
It's going to go twice as far, so it'd be 4 of those.
I have to go, okay, so I've got to double that because it's pointing in the direction where the eigenvalue is 2, so I double. Okay?
And the other way, since it's only just at 1 of those, it's going to go 4 in that direction.
Okay, so I've got 1 of these, I have to go, and instead of going 1, I'm going 4, because that's what the transformation does in that direction. It stretches by a factor of 4. So 1, 2, 3, 4. So we get 0, 8. 0, 8? Yeah. So those of you that got a -1, 9, I think you just counted one too many. So, okay, there was a question, there was a hand? No more hand? Okay. I said 0, 8. I said 0, 8, but I didn't count 0 and I didn't count 8. What did I count? 4 and 4. I counted 4 and 4. So why didn't I say 4 and 4? I could have. So, okay. So the thing here is, if we think about P with different coordinates, so the coordinates of these eigenbases, then we can do the same transformation that we could do very easily with the standard basis. It's easiest for us to think about stretch in this direction 2 and stretch in this direction 4. Okay? And we could do that same thing as long as we could think about P in terms of coordinates of this other basis. So the transformation part, it wasn't that hard. The hard part was, I was thinking about how many of these and how many of these it took to represent P with how many eigenvectors, how many basis vectors in this direction, how many basic vectors of the other basis vectors to get to P. So if I gave you another point, could you do that whole process? I see some ups. Do thumb up, thumb down, or thumb sideways. Thumb up meaning yes, you could do it. Thumb down meaning you couldn't do it. Thumb sideways if you're okay. Right? Thumb 45 degrees. Is that 45 degrees? You know, you're like, I'm pretty good. I'm better than like, I'm not sure. I mean, okay. All right. We actually don't have time to go through another example here, but we're going to go through this, but we're going to the same example, but we're going to do it algebraically. Okay. So what we did was, and mainly we're going to focus on how we did the green and how it connected with the blue. We used the blue thinking to do the transformation. Like the transformation is the same. We can do double this way, stretch this way, or stretch by factor 4 this way, double this way, multiply by 4 that way. But to do that, we had to think about P in a different way. We couldn't think about it as 1, 3. We had to think about it as 2, 1. So let's talk about what we did. We can check, by the way, if you multiply by, if we multiply by 3, 1 here, 1, 3, oops. If you multiply by 1, 3, you do get what? 2, 12. If you multiply 1, 3 here, what do you get? 3 minus 3 is 0. A minus 1 plus 9, 0, 8. You do get 0, 8. So whatever we do, we better end up with 0, 8. So we started with, I'm going to write this 2 ways. So one, I'm just going to write it the way I did there. We started with 1, 3. If we transform it with B, 3 minus 1 and minus 1, 3. If we transform it with B, we get 0, 8. Okay? This was the straightforward multiply it by a matrix strategy that I told you not to do at the beginning. Okay? But when we thought through it with transformations, we did something different. Okay? We started with 1, 3. But then we changed it in our mind about trying to think about it and how many eigenbasis, how many basis vectors of the one and how many basis vectors of the other did it take us to get to 1, 3? So we said, in your mind, I could see you writing this down in your mind. How many 1, 1s and how many minus 1, 1s does it take for me to get to 1, 3? You know, I was being facetious. I know you guys weren't thinking about that in your mind. Okay? But that's what we did. We thought, Porter, can you pull up the thing again? So we thought, how many of these, so are you okay? Okay. How many of these, and that's 1, 1s, right? Those are 1, 1s, at least in the blue basis, I can call those 1, 1s, okay? In the green basis, it's just 1, 0. But in the blue basis, it's 1, 1. So how many 1, 1s in the blue basis, and how many minus 1, 1s in the that I'd label that point a minus 1, 1 in the blue basis, right? So how many 1, 1s, how many minus 1, 1s do I need to take to get to P? Well, I need 2 of the 1, 1s, and I need 1 minus 1, 1s. So that's how we figured it out. We thought, oh, just how many of these diagonals, upper right diagonals, and how many upper left diagonals do we need? It was 2 of those and 1 of those others. But you don't always get situations where you can easily think through it on a grid like that. So we could do it this way, and this will work in any case. How many A's do we need? How many of these do I need? How many of these do I need to get to 1, 3? Because this is the thing. This is in A coordinates, and this is in not B coordinates. This is in A coordinates, but it is the B vector. We just written it as A coordinates, the B eigenvectors, and this is A coordinates. And I could rewrite that whole thing as 1, 1, a minus 1, 1 times AB equals 1, 3. And I can solve it. And there's a very easy way to solve this one. I'm not actually going to solve it. I'm just going to write, well, let's multiply. Let's multiply the inverse on both sides. And if you actually calculate the inverse and multiply that, you know what you end up with? You better end up with 2, 1. Okay? So although we started with 1, 3, we translated it into, and this is in A coordinates. We're thinking of the A grid when I write 1, 3. I multiplied it by 1 minus 1, 1, 1 inverse, and I got 2, 1. And what is that? That is the same point as 1, 3, but in different coordinates. It's in the B coordinate system. Okay, once we had 2, 1, what did we do? Once I thought of this as 2, 1, how did I figure out where it went? I doubled in the first direction, and I multiplied by 4 in the second direction. Okay, that's easy. Okay, I doubled. What matrix doubles in the first and 4 times is in the second? This one, this diagonal matrix. So that'll give me 4 and 4. So this does the transformation. This was 4, 4. In what basis? In B. And then what did we do at the end to get back to 0, 8? If I said, hey, it takes 4 of these, and I want 4 of these and 4 of these, where would you tell me where I was at? I went 4 1, 1s and 4 minus 1, 1s. Where am I in terms of my A coordinates, back in my A coordinates? I'm at 0, 8, right? So how do I take 4, 4, and how do I take 4, 4 in B coordinates? 4, 4 in B coordinates, and get it in the same point in A coordinates. The point hasn't changed. It's actually the same point. The 4, 4 in B is the exact same point as 0, 8 in A. So one of the things that matrix multiplication does, we can think about it as doing a linear transformation. It can also just tell you what the new coordinates are in a different base, the same point. So 1, 1, a minus 1, 1. Okay. So this yeah, so if I have the coordinates in B and I want to go to A, I multiply it by the basis vectors. I multiply the coordinate in B by the basis vectors in B that are written in the A coordinates. So these are the basis vectors of B, but they're written in A coordinates. If they're the basis vectors of B, I just have 1, 0, 0, 1. That doesn't help me very much, right? This is the basis vectors, like this is just 1, 0, and 0. This is, yeah, I want one of the, if you're thinking in B, then all this means is, hey, you went 4 of 1 zeros and you went 4 of 0 ones. Because you're just thinking of the diagonals as your 1 zeros and your 0 ones. So, yes? That's right. We'll hopefully get to that. So, all eigenvalues, I'll say a quick note. All eigenvalues, all eigenvectors are independent. The question is whether you can get enough of them. So the question is whether you can actually get 2, because you might end up with just 1, or n minus something. You might not end up with enough. Okay. So, so what do we do at the end? Well, we can multiply this, and so all of this thing gets us to 0, 8 in A. So 0, 8. So I should do that, gets us to 0, 8. Okay. And since we did these things, and this is an invertible matrix, and these are all invertible matrices in this case. So I multiplied this by an invertible matrix and got 0, 8. I multiplied that same point by an invertible matrix and got 0, 8. So this must have to equal this. So B, so this was my B matrix. Notice this was my A matrix. Okay, so I can rewrite B as B equals, I'm going to call it S. The book calls it P, but I already used P for a point, and that confused, that made it confusing last time. SAS inverse. Yeah, so B equals SAS inverse. When I was in your class, that book used S. So, yes. Okay. Very nice. So the question was, when you're doing this, how do you know what order to put the eigenvectors? So you just have to match it up in the same order with the eigenvalues. So if I put 2 here, then that's in the first column. I put the eigenvector that I got from that's associated with 2 in that first column of S. And if I put, so I put 4 in the second column, then the eigenvector I got when I subtracted 4 off the diagonal and solved for the basis of the null space, that's the one I put in that column. Okay. On the WebAssign, it'll tell you, like, start with the small lambda is the smallest, lambda 1's the smallest value, and lambda 3 is the largest value, or something like that. It tells you, it kind of gives you an order to make it easier for it to grade. So, but it doesn't matter. I could write 4, 2, but these would swap around. So, and these would swap around. You could still do that. So, yes.
What would you do if they were 3x3 matrices and you had to find the inverse of a 3x3 matrices? Because there was a problem like that on the homework, and I didn't know what to do with that.
You mean how to find the matrix of a 3? How to find the inverse of a 3x3 matrix? Yeah. So many years ago now, seems like so long ago, we learned a process for finding the inverse of a matrix, and it works for any size. And So remember yeah, so we augment, you take the matrix that you want to find the inverse of, put it here, augment it with the identity matrix. Then you do row operations on this side. So you end up with the identity matrix over here. And then your other side will be the inverse. You're welcome. Great review. Here?
So how does, so there you have three matrices on the left, one on the right, right? Then on your example, you have four. So where does that 1, 3 go to?
Oh, so we did this all in terms of what happens to a single point. But you don't have to think about a single point. You can just think about this as a general transformation. That's what the book does. You can just think about the matrices in general. And so as long as you can write one, as long as you can find an invertible matrix. Here, I have this on a slide. Maybe. Yeah, so it's easier for me to think about a point, so that's what we did in class, but you don't need to have the point. It'll do the whole plane. Doesn't matter what you throw in over here. What do you multiply the right over here? So in this, I did P instead of S. So two matrices are similar if there exists an invertible matrix P, or in what I wrote on the board S, such that P inverse A P equals B. But you can write, you can write it in different ways. I have like 4 different ways you could write that. You could write it PA P inverse. You could write it A equals P B P inverse. Like you can write this. You can. It doesn't matter if you write S here or S here. It's an invertible matrix. You just S is S inverse, and that doesn't matter. Okay, so the book, I can't remember if the book does S inverse here or S inverse there. It doesn't matter. You still found an invertible matrix that it works. So when testing, this will actually save you some work here. Like if I multiply S on both sides this way, then I get BS equals SA. This is the nice thing to do if you want to test to see if they're similar. Because then you don't have to find the inverse. Okay. So you just have to check to make sure these are the same instead of doing all the work to find the inverse and then making sure that equals B. Yes. Yep, you in the black. So it'll be something. So if you multiply this side by S inverse to get rid of this, so I'm just going to solve for A, then I get S inverse B, and that equals AS inverse. And then if I multiply S on this side, then I get S inverse BS, and I get A. So this is the proof that if B is similar to A is similar to B, because I found an invertible matrix that I can write it as SBS inverse, because I can just say I'll just call P equal, let that equal S inverse, and so then I can write P B P inverse. All right, so I found a matrix. It's just the S over here was the S inverse over there. Did that help?
Because we decided to put B into A's coordinates, but if we're putting A into B's coordinate system,
Yeah.
You would ultimately come up with the same equation if you swap A and B, right?
Well, the S inverse and the S will change. It won't be like these things will be swapped, and you have B in the middle. But yeah. So the nice things about doing this. It makes a lot of sense here to put B in terms of A, because A is a diagonal matrix. It's easy to think about this transformation, right? So let's make sure I can think, let's put the thing in here that's easy to think about. Let's take the hard one, write it like this, so I have something easier. And that's the advantage of diagonalization, is if you can take a complex matrix, write it out here where it's diagonalized. So then This makes it really easy to do calculations, makes it real, you already see where the eigenvalues are, you can already see where the eigenvectors are. This is really, really nice. You can see exactly, oh, it's going to stretch into, it's going to double this, double things in this direction, it's going to 4 times things in that direction. This is nice. It's a lot easier to think than thinking about what to do here. What this piece does here, or what you can think about what both of these do, is they get your coordinates right. So then you can apply this transformation. So the easy transformation. Yes? You could. It wouldn't be very interesting, but you could, because you're going to write, well, yes, you can, but we're out of time, so I'm not gonna, you can stay after, we can do it if you want. Okay, we didn't get to talk about the properties of similar matrices. They'll be on the slides that we share. So there are properties here. And we didn't get to prove any of these. You have a couple proofs on your homework. I'll make a video of me doing a proof of proving that the determinant of A equals determinant of B if they're similar. And I'll post it so you guys can have that. Or I might just write it out and put it on. Have a great day.